All right, the last application is an example of exponential decay. We did an example of exponential growth, and it's very similar, but there's an important thing you have to remember about when it's a decay problem. All right, so we have a fruit fly population. Their density is about 2 million fruit flies per acre. Can't spit that out. An insecticide was used, and it's said to decrease the population by, so again, we're decreasing the population by 25% each week. So again, it's going down by 1/4% every week. Find the equation that models this. What would the population be in 3.2 weeks? Graphically determine though the population is cut in half. All right, so we start off with A, finding the equation. And there's actually two ways you can do this, but I'm going to set it up with the exponential case. All right, so this is the relative percent growth rate, all right, or decay rate in this case, decay rate. And so you need to remember when it's a decay, you're losing that percent. And so when we set up our population formula, so suppose I let capital P be my population, P naught would be my initial population, E raised to the K times time. All right, so time would be my weeks. My initial population, I'm going to leave 2. I'm going to leave it in millions. And so K would be that the fact the population decreases, so it's negative 0.25, right? We always write it as a decimal. And so there's all the parts that I need in order to plug them into my equation. So the population equals 2 E raised to the negative 0.25 times time, and I'm going to leave it in millions per acre, all right, instead of writing out that million there. And so there would be my model. Right? There is the population equation that will model how many fruit flies are left in T weeks. All right, so B, then we'll use it. All right, so time is going to be 3.2, so I plug 3.2 into that equation. And so the population in 3.2 weeks is 2e to the negative 0.25 times 3.2. And make sure that's all up in the exponent. And then I'll just round maybe 1 or 2 decimal places. So that comes out 0.89865. But remember, that decimal doesn't mean 0.8 fruit flies. It's in millions, all right? So it really means 800,000. And so I'm going to round it to, actually, I'm going to round it to 0.9. 0.9 million fruit flies per acre. All right. Or if you prefer, 900,000 fruit flies per acre. All right, the last one, and then we'll solve this. There is a by hand method to solve the last one, but since we haven't really talked about it yet, because we need logarithms to do it, we're going to go ahead and solve it graphically. All right, so we want to know when, so at what time, will the population be cut in half? And so cut in half means, well, I want half of what I started with. And so we started with 2 million. So half of that is 1 million. And so I want to find the time. How many weeks will it take to get to 1 million fruit flies per acre? And so we would, to set this up, you would take your original equation up here, set it equal to 1. So you take your 1 million equals 2e to the k, which is negative 0.25 times time. And we want to solve for t. And like I said, there is a by hand method. Again, we haven't learned it yet, so we're going to just solve it graphically. And so to solve this graphically, in y1, you would plug in your equation 2e to the negative 0.25t. In y2, you would plug in your 1. All right, remember, both those stand for millions. Standard window, I believe, should work just fine. Actually, you might want to zoom in and make it a little bigger, because everything kind of happens around 1 and 2, right? 1 is we got the line y equals 1. There's my 1 million. And then my exponential decay equation comes down. All right, that's at 2. And we're looking for this moment when they intersect. So at what time does this happen? And so you, again, remember you hit your second trace, you pick intersect, first curve, second curve, guess, and it looks like it occurs in almost 3 weeks, a little less than 3 weeks. All right, 2.77 weeks is almost 3 weeks. So it takes it about 3 weeks, a little bit less than, to cut the population in half. If we go down by quarters of a percent of the population every week. All right, so that finishes up 5.3, all right, which we will learn in the next section how to solve this by hand. There is a by hand method, but that's the next section. All right, we will stop there.